This video will show how to graph a basic logarithm using transformations. So first we want to identify the parent function. And the parent function is the basic function that we're starting with, one that doesn't have any transformations. So in this case, imagine that you're removing this negative and we're removing this plus 3. And what remains is our parent. So the parent function will be y equals log base 2 of x. We'll focus on graphing this logarithmic function first. So when you have a logarithmic function, I find it easiest to rewrite the logarithm in exponential form in order to graph it. So to do that, remember we're starting with the base. So that will be 2 to the y power is equal to x. So the exponential form is 2 to the y power is equal to x. And these equations are equivalent. It's just that the exponential form looks a little friendlier and will probably be easier for us to generate a table for. Now looking at 2 to the y equals x, notice that y is in the exponent. So it's going to be easier for us to choose y values rather than x values in our table. So normally we start from -2 to 2 for the x values. We'll put -2 to 2 for the y values. So substituting in -2 for y will give us 2 to the -2 power. The negative exponent will cause this to be 1 over 2 to the second power, which will give us 1/4. So let's plot 1/4 comma -2. We'll just estimate right 1/4 and down 2 somewhere about here on my graph. 2 to the negative first power will be 1 over 2 to the first power, which is just 1/2. 1/2 comma -1 will be plotted here. 2 to the 0 power will be 1. So we have that x-intercept, which will be common for all logarithmic graphs. The parent functions will always pass through 1 comma 0. Then we have 2 to the first, which is 2, and 2 to the second, which is 4. So we'll continue plotting those points. And because I do actually have room, I'll go ahead and go to y equals 3 because 2 to the third power will be 8, and we do have room on the grid that I have to plot the point 8 comma 3. So connecting these points, we can remember a few things. One, that logarithmic graphs have a vertical asymptote. So I like to graph that asymptote in a different color. So we have this vertical asymptote for the parent function. And this vertical asymptote is the vertical line, x equals 0. So here's our logarithmic graph. Then we're going to take this graph and we're going to use our knowledge of transformations to graph the graph of f of x up here. So we have two transformations. One is the negative out in front. We're multiplying by a negative, which is going to cause all of the y values to become negative. So that's going to be a reflection or a flip. We're going to reflect over the x-axis. Think if the y values become negative, then we're jumping across the x-axis. So imagine looking at this point here, which was 8 comma 3. If the y value becomes -3, then that means we're down here and we just jumped across the x-axis. So I'm going to go ahead and do that for all of my points. I'm just going to reflect them across the x-axis. The 0.10 will stay where it is. And then again, I'm just kind of estimating these fractional values. So this blue graph is just the reflection. If you're comfortable doing both of the transformations at the same time, of course, that is completely fine. I'm just going to show them one step at a time. And then we have x plus 3, so we're adding 3 in the parenthesis with x. That's going to impact the graph horizontally, and that is going to be a shift. So we are going to be shifting to the left 3. Because it's a plus 3, that works kind of in the opposite. I'm not going to show why in this particular video. That would be in another video. But that x plus 3 in the parentheses causes a shift to the left 3. And that means that the vertical asymptote will shift left 3 also. So I'm going to graph the new asymptote here, shifted left 3 in green. This vertical line is now x equals -3, and that will be my final vertical asymptote. And then I'm going to move all of my points left 3. And if you want to do the small fractional values, you can. But truthfully, I just focus on the coordinates on the parent function that had the nice whole numbers or the integer values, the ones that didn't have any fractions. I focus on those, and as long as you have the asymptote graphed, you know the graph is going to hug the asymptote, and that is usually going to be good enough. So we'll move our coordinates to the left, 3. And then we will connect the dots using the same shape as the previous graph, which was in blue. We're going to hug that vertical asymptote. It's the same shape, just shifted to the left. And then I always recommend that you go ahead and label your final graph if you have done it in steps like I did, so you know which one is your final answer. Lastly, we'll look at the domain and the range. Now, domain, remember, is all of the possible x values. And that means we're looking left to right. What is the leftmost and rightmost values on this graph? So this graph begins at x equals -3. And because there is a vertical asymptote there, we do not touch -3. So we would use a parenthesis on -3. And then the graph does go forever to the right, which means the x values can get infinitely large. So -3 to infinity. If you want to do x is an element of that interval, you can, but your instructor may or may not require that. Now that was just finding the domain looking at the graph. I encourage you also to think about the domain from the original function that you were given. So that original function, if I rewrite it, was -log⁻² of x plus 3. And what is important to remember about logarithms is that the argument, which I'm highlighting here in blue, the argument cannot be negative, and it also cannot be 0. So in this case, my argument, which is x plus 3, it must be greater than 0 because it cannot be negative and it cannot be 0. So if you subtract 3 from both sides, you get x must be greater than -3, which supports exactly what we had for our domain here. So 2 ways of finding the domain. And then the range, which is all the possible y values, I will find just by looking at the graph. And this graph does go down forever as well as up forever. So we're going to hit every possible y value, meaning that the range will be all real numbers from -infinity to +infinity. And that will be true for every single logarithmic graph. The range will end up being all real numbers if it is a basic logarithm that has just been transformed.